very much. So this is a joint work with Jonathan Bennett, who's joining us remotely. We were playing around with an inequality that's become very central in harmonic analysis and a couple of other areas due to Brascamp-Lieb, called the Brascamp-Lieb inequality. As Tom just reminded me, there are actually two important Brascamp-Lieb inequalities in mathematics, which are not super related to each other, but I will only talk about the harmonic analysis one. Okay, so just to remind you what Brascamp-Lieb inequality that we will be talking about is, it's not a single inequality, it's a family of inequalities, so LP type inequalities that generalize many classical inequalities in analysis. Perhaps the most, the one that you're all familiar with is Holder's inequality, which I will phrase in the following way. You take some functions f1 up to fk on say Euclidean space, and we'll put them in some LP space, LPI, I will only really care about non-negative functions. Of course, Holder's inequality also works for sine functions, but we will mostly focus on non-negative functions here. Yeah, if I want to non-negative functions and you multiply them together and you integrate them, you can control the integral by the product of the LP norms as long as the exponents obey the famous Holder relation there. Okay. And you can just do a slight change of variables. I'll just rewrite this in a slightly different way. If instead of saying that you have LP functions, you have integrable functions, f1 to fk, and you take the product of for each function, you raise it to a certain exponent, one over pi, you can control the product of these, certain, so like a geometric mean of these fi's in terms of the corresponding geometric mean of the inverse of f. Okay, that's an equivalent form. Okay, so we all know that inequality. Another inequality that's almost as well known is the Loomis-Whitney inequality, which is an inequality that holds in every dimension. Let me just state the 3D version, which is already quite typical. So if you have three functions on the plane, f1, f2, f3, and again, let's say they're non-negative and let's say square integrable, and you pull each of them into 3 dimensions in different ways. So f1, you pull into 3 dimensions by making it trivial in the x1 variable, and you only evaluate it at x2 and x3. So that's a function which is L2 in 2 directions and sort of infinity in the 3rd direction. And then you do the same thing but with different coordinates for f2 and f3. So you have 3 functions here. And so Holder's inequality would say that you need all 3 functions to be in L3 in order to test the product. But because of the invariances, and because they're invariant in different directions, you can actually control this product by just the L2 norms, by 3 copies of the L2 norm. And this is not hard to prove. You can prove it, I think, by 2 Cauchy-Schwarzes. So maybe if you're bored, you can expect that inequality. Another way of phrasing it, similar to the way we formulated Holder's inequality, is that if you have 3 integrable functions on R2, F1, F2, F3, non-negative, and for each of these 3 functions on R2, you pull them back to R3 in 3 different ways using 3 different coordinate projections. So there's 3 different ways, if we choose to project R3 to R2. So the picture is that you've got R3 just projecting to R2 in 3 different ways. You take 3 functions, F1, F2, F3. Over here, you pull them back into this big space, and then you multiply them together, and you take a square root. And this particular combination can be controlled by the product of a corresponding combination of the integrals of f. Okay, so this is another way of thinking about the Loomis-Whitney inequality. You can generalize this to any dimension. So in Rk, you take functions of Rk minus 1 in various different ways, and you get this inequality. And in fact, there's an even more general inequality called Finner's inequality, where you have a function where you work in many variables, and you take functions of various subsets of these variables, and there are generalizations. Okay.
Can it also be done with Cauchy-Schwarz?
I haven't thought about that. Okay, so Loomis-Whitney can be proven by iterated Holder in general. Finner's inequality probably is iterated Holder there's a proof. I've never actually looked at the original proof of Finner. I just noticed special case of Brascamp-Lieb, which has a different proof. Okay.
Well, it's still on this one. It's like, did they have some interesting application in mind?
Right. So one consequence of the Loomis-Whitney inequality, so in Loomis-Whitney's paper, they have this, so it's very simple inequality, and they have this immediate corollary, is that the isoperimetric inequality is free over a constant. But if you take a three-dimensional body, that you can control the volume by a constant times the surface area to the three halves. Of course, the full strong isoperimetric inequality, the constant is attained when you're a ball. Okay, but if you just want up to constants, that's immediate from the Loomis-Whitney inequality. Three more lines, but yeah, you apply this inequality where F1 is the indicator function of the projection of one of this so you take a body in R3, you take three different projections, you apply Fi is to be the indicator function of these three projections, you plug this in, you do three lines of computation, and you will get the isoperimetric inequality after a constant. The Loomis-Whitney inequality, Larry Guth had a very nice way of leveraging this to prove a much more general inequality called the multilinear inequality, which has since been used to, for example, prove a decoupling theorem, which applies to the Gowers conjecture. There's the whole tree of things that sort of come out of this one inequality. Thinner, I'm not sure. Probably there's some statistics application, but I'm not sure exactly what his motivation is. Okay. Another famous inequality is Young's inequality. So Young's the sharp Young's inequality. Okay, so the regular inequality of Young, okay, and again, there's two Young's inequalities in this, the convolution one, is that if you have two functions, F1 and F2, let's say on the line, non-negative with some LP, then in some LP classes, then the convolution will lie in some other LP space, LP3 prime, where P3 prime is the dual to P3, and P1, P2, P3 obey a certain scaling relationship. So Young proved this without this extra constant, but then it was observed by Beckner and also by Brascamp-Lieb. Maybe that actually is the original paper with this, that you can actually improve the constant. So if you just use like a standard Rieslow interpolation, complex interpolation, you can get the constant 1, but you can actually get a slightly smaller constant. And this is actually the optimal constant. So this is the sharp Young's inequality, and it is attained when F1 and F2 and F3 are well-chosen Gaussians. There's no F3, there's F1 and F2. And this is the constant that comes in when you plug in Gaussians. And you have to plug in the right Gaussian. So F1 is Gaussian, F2 is Gaussian, but the two Gaussians are related in exactly the right way. And you get this constant. Okay. Again, you can rephrase this in a different way. So now it's a similar situation to Loomis-Whitney, but now instead of 3D projecting coordinate-wise into 3 copies of R2, you have a plane projected into 3 copies of R. By the way, your representation theorists, you recognize the picture I'm drawing as quivers, and there's a whole story there, but we know representation theory in this talk. So R2 you can project into R3 different ways. You can have X, Y to X, to Y, or to X plus Y. So you have these 3 different projections. You don't have to choose these particular projections. You have a Young's inequality for any 3 projections in general position. But if you pick these 3 projections and you pick 3 functions on the real line, let's say non-negative, and you pull them back to the plane in 3 different ways by composing with these 3 different projections, then again, a certain sort of like geometric mean type expression, like product of roots of these pullbacks, can be bounded by a certain constant times the corresponding combination of and it's the same constant here. And again, if you have F1, F2, F3 as well-chosen Gaussians, then you have equality. And this is an equivalent form. Basically, you just use the dual. This comes from the duality between LP3 and LP3, and it's a little bit of algebra. Okay, so this is the Young's inequality. So now those are 3 sort of motivating examples of the general Brascamp-Lieb inequality, which I will now say. Okay, well, actually, I'll make a definition. So the 3 inequalities that I just wrote, you can generalize in kind of an obvious way. So if you have some Euclidean space, which you think of as a big space, and it projects onto many, many smaller spaces. Okay, and using various linear maps, B1, B2 up to BK. So if you have a bunch of linear maps from a big space to a lot of smaller spaces, and you have a bunch of exponents, C1 to CK, you can define the Brascamp-Lieb constant associated to this data. Okay, so the data is a k-tuple of linear maps and a k-tuple of exponents, and it's the best constant such that whenever you have non-negative integrable functions on each of the base spaces here, if you pull them back to RD by composing with these BIs, and then you raise them to certain powers, that you can control the product of these powers of these pullbacks by the corresponding combination of the original integrals times a constant. And the best constant, we just call the Brascamp-Lieb constant. Boldface B is just my notation for the k-tuple B1 to BK, and boldface C is my notation for this tuple. So this is the data, and this gives you a constant. So you can always define this constant, but it could be infinite. Right? So sometimes you don't have, for example, Young's inequality and Horner's inequality. You only have that inequality under certain conditions on the exponents. So this quantity could be finite or infinite. Okay, so this is not yet a theorem. This is just a definition that every data there's a number, possibly infinite. And then you can specialize this. So you want this inequality to hold for all non-negative Fi, and then the best constant we call the Brascamp-Lieb constant. Or you can specialize. You can restrict the Fi's to all be Gaussians, and that will give you a smaller constant, which you might call the Gaussian Brascamp-Lieb constant. Okay, now so this one is easy to compute in principle because we know how to integrate Gaussians, and you can multiply Gaussians and get more Gaussians. Okay, and everything here is very computable. This is okay. Although actually, this is in principle computable. Actually, it was only recently that we understood that this was actually like practically computable, but that's another story. Okay, so we have these two basic definitions. But actually, after giving you these two definitions, I can give you the fundamental theorem of Lieb that they're the same. Lieb proved this wonderful theorem that that the optimal constant for arbitrary functions for any kind of Brascamp-Lieb type inequality is the same as the constant for Gaussians. So if you want to prove the Brascamp-Lieb inequality, it suffices to test it on Gaussians and prove it in general. There's a little subtlety. This doesn't mean that the inequality is optimized by Gaussians. I mean, it so morally does. Sometimes, so in the case of Young's inequality, some Brascamp-Lieb data are what are called Gaussian extremizable, or extremizable, but there are some functions which actually attain the extremum. And I think if they are extremizable, then they are also Gaussian. No, that's not quite true. Okay. Yeah, not all data is extremizable, not all data is Gaussian extremizable, but okay, there is an implication one way, but I forget exactly which way it goes. So even if there is no extremizer for these inequalities, it is still the case the best constant is the same. Of course, they could both be infinite too. We also know now when it is finite and when it's infinite. Strangely enough, that took that was a basic question. Somehow it wasn't answered until much later. Okay, so John and I and Tony Carpy and Mike Christ, we showed when this constant is finite. So first of all, there's a dimension condition. That the dimension here has to relate to the dimensions here and the exponents, and so there's an actual sort of dimensional analysis condition, which is this relationship. And then this relationship has to be stable. Stable actually in the sense of algebraic geometry, that's another story. Okay, that if you restrict to RD to any subspace, and then you restrict all these spaces to the corresponding images, then this equality must become an inequality in the right direction. If that's not the case, you can create counterexamples by choosing functions f1 and fk that are sort of localized near each of these subspaces, and you can do a short computation and see that you get a counterexample. Slightly less obvious is that conversely, if you have this stability, then you have this inequality. That you can prove by actually just Holder, lots and lots of Holder, if you don't care about getting the right constant. Okay, which actually means, to answer your previous question, I think thin is an inequality. If you're not, actually, if you are willing to have a bad constant, I think you can prove it just by Holder. And then you can move the constant by the tensor power trick. Okay, that's yeah. So probably you can actually prove Holder thinner directly by Holder. Okay. All right, so we know that things are finite. What else do we know about the Brascamp-Lieb constant? There's one case where things are really nice. There's one case called the geometric case, where all these BIs are what are called co-isometries. Basically, I think of it as orthogonal projections. That they're orthogonal in one direction. That if you multiply them on the right by the adjoint identity, the adjoint is isometry, they're called co-isometries. So this is the basic examples are orthogonal projections, and if and then if you do it the other way, in fact, well, those are not projections, but if you take bi star bi, those are projections. But those projections have to add up in a certain way. A certain combination of those projections have to add up to the identity. If you are in this case, called the geometric case, then the inequality simplifies quite a lot, and the Brascamp-Lieb constant is exactly 1 in that case. This was observed by Ball, and there's another proof by Frank Barth. In fact, this case is somehow the most important case. Like the general Brascamp-Lieb inequality can be reduced after some linear transformation decompositions into this case in some sense. Every Brascamp-Lieb inequality is somehow a direct sum of or semi-direct sum of sort of linear transformations of this case. This is kind of the normalized case. And there's many nice proofs of the Brascamp-Lieb inequality in this case. In particular, there's a very nice heat flow argument that works in this case, using just the usual Euclidean heat flow. If you want to put the Brascamp-Lieb inequality directly, you have to use a heat flow adapted to your problem. But you can just, in the geometric case, you can use standard heat flow. There's some other nice results. We now understand these constants, how they depend on parameters a bit better. So there was an important continuity result a few years back that if you wiggle the B's a little bit, the Brascamp-Lieb constant doesn't change very much. So it's actually depends continuously on B as long as you restrict to the domain where it's finite. Which sort of opens up the possibility that it can be computed in reasonable time. And then subsequently a group of computer scientists, actually Gowers, Vigdisson, observed, okay, this is an oversimplification. Okay, but roughly speaking, if you want to compute the Brascamp-Lieb constant to any accuracy, you can do it there's a polynomial time algorithm in the accuracy in the data. So,
is the finiteness really? I mean, like,
I guess if you define the topology.
I mean, if it is infinity and you approach it, it will go to infinity, I would imagine, or is that false?
Probably. I don't know. Maybe my co-author can rescue me on that one. But that sounds plausible. Maybe there's probably semi-continuities. There's probably some Fatou lemma thing that gives you semi-continuity, which maybe implies what you say, but I can't figure out in my head which way the body goes right now. Yeah, there's probably more continuity properties than this, and I think people have also started looking at you can ask for like how continuous this is. That's a whole other talk. Okay. I'm sort of giving you some flavor of the type of things that are known about this concept. Okay. All right. Yeah. So they're connected to many areas of mathematics in many ways. Okay. So first of all, like there's all kinds of ways to prove these inequalities, and all kinds of pretty much almost any technique that you can use to prove inequalities can be somehow applied here. That's a bit of exaggeration, but yeah, there are proofs using transport. There are region proofs. My favorite is heat flow. There's a proof using entry methods, entropy methods, proofs using operator scaling. Yeah, and they're connected to all the other kind of famous inequalities in analysis pretty much. So I mentioned a whole bunch already. There are also connections to Brun-Minkowski, some of the entry power inequality. And as I said, it connects to the multilinear K inequality, which is one reason why I like these inequalities, because they connect to lots of other things in harmonic analysis, like decoupling theorems and distribution theorems. Again, these are all, each of these is again a separate talk. Right? So these are just sort of background things. This is not really what I wanted to talk about, but just to convince you that Brascamp-Lieb inequalities are a thing. Okay. So they're a multilinear inequality. You have multiple functions as input, and you take one low dimensions, and you take one function as output. So what did I put on my next slide? Oh yeah, yeah. So people have studied this. There's a huge literature on these inequalities. There are many variants of this inequality. There's something called the entropy Brascamp-Lieb inequality, where you place the LP norms by entropies, like L log L type norms. There's something called the reverse Brascamp-Lieb inequality, introduced by Barth, which is a bit hard to explain. Yeah, it's kind of a tropical inverse here that you have some some soups and things. And then once you have this continuity, you can start generalizing the Brascamp-Lieb inequality to nonlinear Brascamp-Lieb, where these B's are no longer linear transformations, but nonlinear transformations. The continuity is an important first step to start doing that. That's important for many applications too, especially in harmonic analysis. So yeah, we're just sort of, so we have this sort of extra contribution to this. We discovered one extra twist that you can make to the Brascamp-Lieb inequality, which actually is kind of obvious in retrospect, but it doesn't seem to be in the, well, it's sort of implicit in some literature, but which we call the adjoint Brascamp-Lieb inequality. So if you have a linear inequality, then we are all familiar that linear inequalities often have adjoints. If you have a linear estimate for one Bimax space X to a Bimax space Y, then and it's bounded, then the adjoint map exists, or enough hypotheses at least, and it should map the dual space of the range to the dual space of the domain with the same constant. Okay. So people are very used to taking adjoints of linear inequalities. It's less obvious how you can get adjoints of multilinear inequalities in general. And I mean, you can try, you can sort of abstractly do some things, but but in the case of Brascamp-Lieb, there's one nice extra identity in Brascamp-Lieb that makes it more favorable to take adjoints. And so this is so instead of starting with functions on little spaces and pulling them back to create one big function and estimating that in terms of or little functions, you can take adjoints and instead start with a single function on a high dimensional space, push it forward, take marginals, push it forward towards little spaces and try to control a function on a big space in terms of all its marginals. So there's a whole family which is potentially useful, and we have one or two applications so far, and hopefully there'll be more. Okay, so so the usual Brascamp-Lieb inequality is phrased in terms of pullback operators. Okay, so whenever you have a function on a small space, you can pull it back by one of these linear maps, and you get a function on a big space, which is sort of constant in some variables, but retains the features of your original function in the other variables. So that's a pullback operation, just composition of BI. Okay, so that's a linear map, so it has an adjoint, and the adjoint is called the push forward map. So conversely, if you have a function on a big space, you can push it forward. You can think of it as a probability measure, like a mass distribution, and push it forward. Let's say, for simplicity, that we want to deal with non-negative functions, non-negative measurable functions, and you can just define it to be the adjoint. So it's whatever function which, when you test it against any function on the small space, that's the same as testing your function f against the pullback functional space. Okay, so by abstract nonsense, this thing exists. And because these are linear maps, I mean, there are explicit formulas for this. So just to give one very, very simple example, if you take a projection from R3 to R2, which is just projecting out the x1 coordinate, then the push forward of a function, a three-dimensional function under this map, is just integration under the variable in the kernel. So this is basically just integrating out the kernel of the linear map. Okay, so so that's sometimes what you call a marginal. So f is a probability measure on three variables. This would be the marginal distribution of just the last two of your three variables. Okay, and because you're non-negative, Fubini's theorem basically tells you that this push forward preserves mass. Okay, the push forward is of f as the same L1 norm as the L1 norm function. Okay. Which of course is adjoint to the fact that pullbacks preserve at infinity. Okay, so these are push forwards. Okay, so you can try to write down a notion of adjoint. Okay, so it took a while to actually find this. Okay, so once we make the right definition, well, okay, the hard thing was to find the definition. Okay, yeah, so you get the same setup as in the forward Brascamp-Lieb inequality, where you have a whole bunch of linear transformations, B1 to BK, small spaces. So that's part of our data. We again have some exponents CI. We also now have some additional exponents theta I. We can weight the marginals in different ways, and then an additional exponent P. So there's actually now 4 pieces of data that show up in particular adjoint. So the original Brascamp-Lieb data B and C, but then some other exponents theta and P. And then once you have theta and P, there's some additional exponents PI, which are related to all the previous data by a certain formula, which is displayed there, but you shouldn't pay attention to it. And so the type of inequalities we will care about is that you now have one function on the big space, and you push it forward, and it's in some LP, and you push it forward to each of the small spaces using these maps B1, B2, and so forth, and you get functions in the small spaces, and you compute the LPI norms of these guys, and you want to control the Fs by a suitable weighted geometric mean of these push forwards. And of course, you want to be homogeneous. If you want this to be so homogeneously accurate, you want the theta to add to 1. So yeah, so the same number of Fs on both sides. And so I just defined the adjoint Brascamp-Lieb constant with this data to be the best constant for which this inequality is true. So this is a definition to be finite communicant. And you can also define the Gaussian adjoint Brascamp-Lieb inequality to be the same thing, but where you only test on Gaussian. So again, that's
CI does not appear explicitly.
not explicitly, yeah. So the CIs affect the PI. So those PI is shorthand for whatever solves this equation. So I mean, I could have not had the PIs here. I just plugged in whatever this shows up there. But yeah, so the C's are in there. This is just what comes out of the calculation. Okay. So yeah, these actually are the parameters, but okay. The most important ones are still B and C. The theta and P are additional parameters. Yeah, so basically it turns out that each Brascamp-Lieb inequality doesn't have a single adjoint. It has actually multiple adjoints, and you get to pick some additional parameters to select the adjoint, which gives you a bit of flexibility. It also gives you a bit of loss. Okay, so in the linear case, an inequality and its adjoint are completely equivalent. They're not quite equivalent here. So what we do show, our main theorem, is that for any choice of this data, the adjoint Brascamp-Lieb constant is bounded above by the correct power of Brascamp-Lieb constant. It's Brascamp-Lieb constant to a certain power, but it's also bounded below. So it's not quite equal, but it's bounded below by the same constant times a certain loss. So there's a certain constant loss that depends in a messy way on all the parameters. But up to constants, this adjoint Brascamp-Lieb inequality constant is basically as the natural power of Brascamp-Lieb constant. And the same is true for the Gaussian. But so if you check the Gaussian, it's also standard-enriched by these constants. So up to constants, all these four things are equivalent. Although I think we know that every single inequality can be strict, which is annoying. So the situation is not as pretty as with Lieb's theorem, where we have this perfect equality. And that's a beautiful theorem. We kind of only have equivalence of constants. But in particular, one corollary of this is that this adjoint inequality I just mentioned, this constant is finite if and only if the Brascamp-Lieb constant is finite. And we have a criterion for that. So we have a pretty good criterion for telling you when you have, if you don't care about exactly what the constant is, I can tell you when a function is controlled by its marginals. And I should mention, this is only for non-negative functions. Of course, you can't expect this to be true for sine functions because you can have a sine function where all the marginals vanish by cancellation. So you can't expect to control function by its marginals if you have cancellation. But if you have non-negative functions, then you can control function by its marginals. Another thing is that the only way that these constants, these inequalities can have a hope of working actually is if LP is less than 1. For P bigger than 1, you can easily check that there's no way you can control an LP function by its marginals. For P equal 1, you can because the marginals preserve the L1 norm. So if L1 here, if P is 1, then Pi is also 1. And then you just have equality here with a constant 1 here. For P bigger than 1, actually, sometimes you can get the reverse inequality. Sometimes you can get a lower bound of the LP norm. It's actually lower bounded by the LPI, so it's marginals. So these inequalities are actually mostly, they're only available for P less than 1, which is maybe one reason why they haven't shown up so much in the literature, because LP norms will be less than 1, not as popular. But they are there, and so everywhere you have a Brascamp-Lieb inequality, you have this family of adjoint inequalities. Okay, all right, so that's our main theorem. So for instance, you can just go through each one of the previous inequalities and find the adjoints. Okay, so you take the adjoint of holder, I think you get nothing interesting, you just get another holder inequality. The first non-trivial thing you can do is you can take the adjoint of the Loomis-Whitney inequality. And so just to give you a flavor of what adjoint inequalities look like, this is the adjoint Loomis-Whitney inequality, that if you have a function on R3, non-negative, and you just take its marginals, you project it, you squish it onto 3 different coordinate planes, and you get 3 functions F1, F2, F3 on R2, then for any p less than 1, you can control the LP norm of the original function by the appropriate LP norm. This is also something less than 1 of the marginals. Okay. And this, by the way, also provides a separate, well, it's not so surprising, but it also provides a proof of the same thing I said before, that the isoperimetric inequality is true of the constants. If you apply this adjoint inequality to indicate a function of any 3-dimensional body, you will get pretty quickly a weak isoperimetric of the constants. Okay, and this inequality is completely sharp. If you apply it to a box, indicate a function of a box, you can just check that both sides are equal. All right, and this is the 3D inequality, and you can do similar things in higher dimensions. All right. So this is a typical example of what these adjoint inequalities look like. There's a cute application of this, which is not ours actually. Yeah, so there's an application of one of my favorite norms in analysis, which are these Gowers uniformity norms, which if you've been in this program, you've probably seen many, many times. All right, here's the formal definition. Okay, so if you have a function on a, say, a finite Euclidean group, and you want to define its Gowers UK norm, what you can do is that you differentiate it k times in a certain sense, and you take the average value of its derivative. Right? So here, the derivative is in a multiplicative sense. You multiply your f by its shift. Here I have a real value function, a complex value function, take a complex conjugate here. But you take this and you so there's something that's a nonlinear derivative. It's the quadratic operation, and you do it k times. So you're basically taking 2 to the k copies of your function together, averaging over parallel pipets, and then taking a certain average of that. And that's called the Gowers uniformity norm. It's very important in analytical combinatorics and ergodic theory. That's another series of lectures for that. Okay. For example, the U1 norm is actually just the mean. The U1 norm function is just mean, and the U2 norm happens to be you're averaging your function on parallelograms, which is the same thing actually as taking the L4 norm for your transform. Higher norms are less well understood. That's a whole different story. So these are norms that people care about. If you apply it to the indicator function of a set, this norm is basically counting how many k-dimensional parallel pipets you can find inside the set. So it has a combinatorial interpretation. Now it's related to because they shifts. These are not Holder type. These are not LP norms, but they're related to LP norms. Yeah. So actually, if you play around with Holder's inequality a little bit, you can find that each of these norms is bounded by a certain LP norm of your function. So in applications, we often only care about bounded functions. If a function is bounded, then all these norms are bounded as well. But actually, each of these UK norms can actually handle a certain amount of unboundedness. The kth Gowers norm, if you just play around with Holder's inequality enough times, you'll find that it's bounded by a certain LP norm. For example, the Gowers U2 norm, which is the U1 norm is bounded by the L1 norm, the U2 norm is bounded by the L4 thirds norm, which is also Young, and so on. And so one nice application of the adjoint Loomis-Whitney inequality is that the UK norms obey the same Holder inequalities that these norms do. So these norms are not equal, but they obey parallel estimates. So these particular family of norms obey a Holder inequality, and so do these. So there is a Holder inequality for the Gowers norms, which I believe is implicit first in somewhat Koshkredov, and then also it shows up actually in Freddy, and then but maybe only for some UK norms. But actually, it's a nice corollary of the adjoint Loomis-Whitney inequality that these Gowers norms, if you apply to a non-negative function again, so there's no cancellation. Which is a bit unfortunate actually, because actually half of the good application of Gowers norms come from functions with cancellation, but without cancellation, it's still interesting. It's more combinatorial, that they obey Holder type inequalities, that this function, that there's some log convexity to this UK norms, that if you have 3 consecutive UK norms, that the UK norm, the intermediate UK norm is controlled by a geometric mean of the other of the extremal UK norms, where the exponent is exactly what Holder's inequality would predict if you pretended that UK norms were somehow analogous. is nice consequence. Combinatorially, this says that, for example, if you have a dense set with a lot of parallelograms inside it, then it also has a lot of parallel pipets inside it. Things like that. Which is kind of a useful fact. Okay. Yeah, so it's the proof is well, okay. The proof is a page of calculation. You just have to apply the Loomis-Whitney inequality to exactly the right function, and it turns out to be you take the what's called the K-point correlation function of one the Gowers version of that for every shape of parallel pipet, you translate the parallel pipet over all the whole group into the averages, and you and that gives you a function of k variables, and you apply this Loomis-Whitney inequality. You have to replace the reals with a finite group, but actually, in the case of Loomis-Whitney, the inequalities that are true for R are also true for finite group. You just apply that, and you get this application. Okay, there's another connection. So this adjoint inequality, it's an inequality when P is less than 1. When P is equal to 1, it's actually an equality because the L1 norm is preserved by push forwards. So okay, so whenever you have an inequality which is an inequality for some P, but at a special P like P equals 1, it's the equality. There's a standard trick is that you can try to differentiate your inequality at the place where equality holds, and you can get another inequality. You can get sort of a linearized inequality, log linearized actually, around that exponent. Okay, this is called the replica trick, but okay, so this is differentiating the LP at P equals 1. The thing is that if you differentiate the LP norm at P equals 1, you basically get the entropy function. So the entropy of a function f, same or negative, is the inverse f log f. If say f is a probability density function. And so you can take this adjoint inequality and you differentiate it at P equals 1, and you get what we could call the entropic adjoint Brascamp-Lieb inequality, but this was already known. Okay, so this was previously observed by Carlen and Cordero-Erasquin, that if you take any probability density function and you want to understand its entropy, you can lower bound its entropy by certain combinations of entropy of its marginals, up to a constant, which is the log of the Brascamp-Lieb constant. So this was a known inequality. In fact, this is actually equivalent. Yes, in fact, this constant is best possible in this case. So if you can prove this inequality for some fixed specific constant, you can integrate it in some sense and rederive the Brascamp-Lieb inequality. So this is the entropic form, entropic adjoint form of the Brascamp-Lieb inequality. There's also a forward form, which is a bit more complicated. But this is somehow the infinitesimal version of our inequality. You can think of it probabilistically, just an equivalent form. If you have any random variable if you have any random variable in RD and you just project it, applying various linear transformations, you can bound the entropy of your big random variable by combinations of the random variable of these projections up to a constant which depends on the Brascamp-Lieb constant. So just to give you one example or two examples. So the entropic adjoint Loomis-Whitney inequality is the statement that you take any three random variables of real random variables x1, x2, x3, the entropy of the triple of these three random variables jointly is bounded from below by a certain average, by 3/2 the average of the pairwise entropy of the two random variables. This looks like it should follow from the Shannon entropy inequalities. It doesn't quite directly follow from Shannon. Maybe it does if you're really clever. But anyway, yeah. So if you have large entropy pairwise, you also have large entropy for triples, and similarly for higher, you have similar inequalities for higher random variables. And there's also an entropic adjoint Young inequality. Here's a typical one. You have two random variables x and y, and you know that x has large entropy, y has large entropy, and x minus y has large entropy. You don't assume they're independent; they can be coupled. But as long as these three combinations have large entropy, then also there's a large joint entropy, and you gain a certain constant as well.
Can you have a similar result to say for three variables?
Probably, yeah. So I mean, yeah. I mean, there is a general inequality of this type that you can have any variables and predict any combinations and any coefficients here, as long as this coefficient is positive.
I mean, that formula is beautiful, but then for three variables, you don't. That's what is the.
I could compute it just, but I need
But
to.
will it be nice? We don't.
Not quite as nice as half log 2, but it would be log of some ration. It would be log some linear. Yeah, it's like it involves things like pi log pi. Yeah, yeah, it's basically the log of well, actually, no, I didn't.
Okay, I remove my question because you will start looking.
Yeah, you can change these 2/3 with other numbers that add up to 2, and then this constant changes. Yeah, you can have multiple ones. These are just examples of this very general inequality that shows up. Okay. Okay, so maybe just a few words about how we prove these things. Okay, so so the main theorem, as I said, was just that these 4 things are equivalent or are up to constants. So one of them is trivial. Okay, so the Gaussian adjoint Brascamp-Lieb is trivially bounded by the full adjoint Brascamp-Lieb constant because this is just the best constant for special case functions. So that's not an interesting one. This is basically just Holder's inequality done cleverly. I mean, how do you derive an adjoint inequality? Inequality in the linear case, you apply Holder and basically that's it. Holder and maybe the converse top of it. So that's basically what we do. So you have a function f and you have what's marginals. Basically, to prove the adjoint Brascamp-Lieb inequality from the Brascamp inequality, you derive you apply the forward Brascamp inequality to the functions that are the push forwards of your function on the big space, raised to the right power, which happens to be pi. So if you apply forward Brascamp-Lieb to these particular functions and just plug it in, and you do 5 lines of calculation, you get this inequality. The main thing, the main observation is that there's this one extra property. These push forwards obey one identity, which arbitrary maps don't. And so you do get a good adjoint in this case, whereas for general multilinear inequalities, you don't really get a good adjoint. So the one identity, which is kind of trivial actually, is that if you have a function f in Rd, you push it forward. I forgot to. Okay, if you push it forward to a small space and then you pull it back, and you raise it to the power p minus 1, and then you multiply by your function. That's the same actually as just integrating p minus 1 copies of this. Maybe instead of let me just show you a special case of this, maybe which is more revealing. So the function f. Let's say projection. Margin, which is just integral 1. Okay, what I'm trying to say here is that if in R3 you integrate the push forward with some power times the original function in all 3 variables, that's the same thing as in 2 variables integrating the push forward. P in 2 variables. So this is not a deep statement. This is Fubini's theorem. Okay, because if you integrate this next one first, you just get one more copy of this push forward, and then okay. So there is this sort of trivial extra fact that these push forwards obey, and there's a corresponding thing which I didn't quite write down correctly here. I think I wrote kind of correctly here, but not. Okay, yeah, that these marginals obey a certain extra identity involving the fi's and f, and if you combine that with what you get when you plug in these functions into the Brascamp-Lieb inequality, and you apply Holder's inequality after about 5 lines of calculation, you can look at this value. So the more difficult thing is to get the matching lower bound up to a constant. Initially, we thought actually that maybe these were equal, but we have examples now that there was a strict gap, unfortunately. Okay, but they're equal up to constants. And this is easiest in the model case. So I said there was one model case. Yeah, so there's the one model case that people understand pretty well, which is what's called the Gaussian extremizable case, where there's we understand Brascamp inequalities quite well when there's some choice of Gaussians that make the inequality attained over equality. Because then what you can do is that you can normalize all the Gaussians to be standard Gaussians with covariance matrix identity. And normalizing that is actually equivalent to making the inequality a geometric inequality. So where these conditions I said before, whether these are co-isometries and the corresponding projections normalize some up to identity. So that's the simplest case. And in the Gaussian extremizable world, you can always normalize to that case. And then actually, it's very easy. Once you've normalized, you just plug in. You can get lower bounds. Or, this constant is 1, and you can lower bound the adjoint Brascamp-Lieb Gaussian constant just by plugging in a Gaussian and computing, and you get this. So so in the Gaussian extremizable world, you're fine. Now, not all inequalities are Gaussian extremizable. There is this question. I don't think that John and I have achieved consensus on this, but we think that the Gaussian extremizable data are sometimes dense but it depends on what dense means in the space of all Brascamp-Lieb data. But you should be able to approximate, even if you have an inequality where there is no Gaussian extremizer, you should be able to perturb it and find one which has a Gaussian extremizer. If you could do that, because we know that certain constants are continuous or semi-continuous, we should be able to deduce the general case from the Gaussian extremizer case by some sort of limiting argument. So we tried doing that. We were not able to complete that argument. There might still be a proof, but actually there was a shortcut that bypassed all this. So rather than mess with all these exponents, there are these things called local Brascamp-Lieb inequalities, where you don't test over all functions which are non-negative, but only functions that are called type G. They're functions which are convolutions of a Gaussian G and something non-negative. So they're kind of, it's like discretizing your problem because you're sort of blurring things out at scale G. And if you blur things out this way to sort of localize, you can call it local or discretizing. It sort of depends on your point of view. But if you localize these inequalities, then they automatically become Gaussian extremizable, it turns out. There's enough compactness now that extremizers exist. And then, so actually, rather than try to figure out whether extremizable data are dense, you can just take any data, extremizable or not, blur it out a little bit to localize it, and then it's automatically extremizable by compactness. You can apply the argument I mentioned previously to get the right inequality for the local inequality, and you take a look. So it's a kind of standard sort of juggling with epsilons type of argument that you often see in analysis. So that's how we get that lower bound. Yeah. So that's where we're at right now. We're still working on it. I don't have a preprint yet. So still trying to see this further things we can do with this inequality. Yeah, at first we thought that all these, there's not really some nice inequalities here, but every single inequality, I think that I mentioned in my main theorem, we had examples where they're not strict. And in particular, the adjoint, so whereas for Brascamp-Lieb inequalities, you expect Gaussians to be extremizers, it does not appear in general that Gaussians are extremizers for our adjoint inequalities. Somehow, the reason why there's not a tight correspondence is that to derive the adjoint Brascamp-Lieb inequality from the forward Brascamp-Lieb inequality, we are applying forward Brascamp-Lieb to a very special class of data. The data where the functions that you input come as marginals from a single function. And that's not a complete class of all test functions. And so we're taking the Brascamp-Lieb inequality, we're kind of restricting the data set to a kind of weird nonlinear subspace. And in particular, it seems to miss the extremizer, like the clean Brascamp-Lieb inequality can be, the extreme can be attained for some nice Gaussian data, but our subspace that we're restricting to kind of can miss this these perfect extremizers. And so either extremizers might not exist at all, or if they exist, they're just nasty. You know, they solve some Euler-Lagrange equation, but they we are increasingly pessimistic that they have clean formulas. So we don't quite understand what's going on as to exactly how we can extremize it. So the theory is a bit nastier, but we still think that these inequalities have some potential for some applications. We have we would very much like to connect these inequalities to something called the reverse Brascamp-Lieb inequality of Bath. We can't quite do that, But there's something called the forward reverse Brascamp-Lieb inequality that combines the forward Brascamp-Lieb inequality with fast reverse Brascamp-Lieb inequality. That one we may have a chance of somehow combining with what we're doing, and then we can somehow take a limit, get back to the reverse. So yeah, we're still trying to figure out how this inequality fits in with the other web of other inequalities here, but this is where we're at so far. So thank you very much.
Questions?
Yes.
The entropy inequalities remind me of Shearer's inequality, which goes the other way.
Yeah.
I wonder whether there's more connections there.
Okay, you have to remind me what Shearer's inequality is.
Shearer's inequality says that if you have n random variables, then the joint entropy is bounded by the sums of entrophies of some of them. So you take the entropy of this bunch and that bunch and that bunch, so long as the bunches that you take cover each variable the same number of times, and then you divide by that number.
Okay, that might actually be.
It's the other direction.
I'll have to check. I'm pretty sure I have this the right way around.
At least for the bottom line, I think it's.
I think. Well, okay. I possibly I made a sign here. Okay, I mean, I can't imagine that there's two inequalities of connecting these relationships that are. Okay.
Loomis-Whitney generalizes Shearer, or the other way, at least when you have a density function, when you speak of random variables.
Okay.
This question can't be, if you take x1 and x2 to be equal, and x3 to be all diagonal, then this is also left hand side is 1 and the right hand side is 3
Okay. This, yeah, okay, thank you. Yes, I think I may indeed have, but then, okay, I will go home and check this. Yeah, probably what happens, I made a slight mistake here, and probably this inequality is indeed Shearer's inequality. I will check it. Yes, David.
You said there's an algorithm for computing Brascamp-Lieb constants. So is there one for the adjoint case?
Not up to constants. No. Yeah, it's just a nasty externalization problem. I mean, it's not even clear that there's a finite algorithm currently. Yeah, no, we haven't got that far yet. It may not be a good question necessarily. I mean, I'm not saying that. I mean, the Brascamp-Lieb constants seem to have some nice geometric interpretation. And as I said, the adjoint ones, they're coming from kind of restricting the Brascamp-Lieb inequality to a certain class of inputs, which is sort of necessitated by the application, but it loses some of the geometric structure. And so, you know, so whereas the Brascamp-Lieb constants in, like for Young's inequality happen to be some nice numbers, I think in general they could just be like arbitrary transcendental numbers with no particularly good interpretation. But they could be computable. We are looking as to whether extremizers exist. I mean, whether there's some sort of compactness theory, which would at least maybe say that they are computable in some computer theory sense, if not a complexity theory polynomial time.
So it's on the Gowers norm Holder inequality. If I do that over the reals rather than over a finite group,
Yes, also true.
can you get a sharp constant?
Good question. Yeah, I know that over the reals you can gain a little constant here. Yeah,
Yes.
for example, in U2, that's the sharp loss of them. That's yeah. In general, I think that's it. Yeah, Tanya Eisen and I had a result. For higher UK, actually, the sharp constant is not known. I mean, we know it's less than 1. We can prove on the reals. Oh, hang on. That from the Brascamp-Lieb inequality is actually.
That should tell you.
Yeah. No, that constant is known. Yeah. Right. Okay. So theoretically, of the reals, maybe there is actually a gain here. Yeah, I don't know if the constant has to be 1. That's a good question.
I think it should be less. I have no idea if it's possible, practical to figure out what it is.
Certainly, I can't think of an example which would. So on a finite group, you set F to be an indicator function of a subgroup and the equality chain, but we don't have any subgroups of any positive finite measures. So probably that's indicate. Yeah, if you plug in Gaussians, I'm pretty sure you will not get equality here. So that suggests the constant structure less than 1. Yeah, that's a good suggestion.
For the Loomis-Whitney inequality, I remember if you also average over all the possible coordinate systems, it's possible to refine a little bit the constant, and that there's some refined inequality that achieves equality for the sphere, and that maybe recovers the parametric inequality.
Oh yeah.
Do you have? Are there versions like this for Brascamp-Lieb and adjoints and so on?
It's a good question. I do not. There is something called the Brascamp-Lieb inequality on the sphere, which may not be what we're talking about. Yeah. Okay. I have not thought about what happens when you average over the B's. Principle, every time you have a modeling inequality, you can try taking an adjoint and you get something like what I said, as long as you have an extra identity of this type. Yeah, I don't know what you get. That's a suggestion. Yes, Betty.
For this geometric case, can you convince me, every time I see this written down, I think it's a category error, right? Because there's no inner product on RD when there's a problem that suddenly this inner product has appeared.
Right.
Is there a right way to think about that?
Okay, so if your inequality is externalized by a Gaussian is given by an inner product. And so you basically what we're doing is that we're imposing the Euclidean jump structure on each of the spaces that comes from the natural Gaussian associated with spaces. And the fact that it's Gaussian externalizes, actually, if you work out the order of the Lagrange equations, is telling you that is geometric data.
I see. So finding the correct inner product in RD that makes that geometric condition true is kind of just a rephrasing of the problem of finding a Gaussian externalizer.
Exactly.
Okay, if there are no other questions,